So here's a non-vector example of things that behave like vectors. And so we can see how this general theory that we have developed, this abstraction, is very powerful. Here's a problem of we want to find a quadratic function, a polynomial of degree 2 or fewer that best fits e to the x. E to the x is a function that is difficult to compute. E is an irrational number, but quadratic functions are easy to compute. We can compute polynomials by doing pluses and timeses, and even powers, but that's still just lots of timeses. E to the x, not so. And so one of the ways we can compute e to the x, or it's computationally more efficient to approximate e to the x, is to find the polynomial of closest fit. So to do that with degree 2, we are going to see about this problem. Now up here is we're going to find the coefficients. The a's are the unknowns. A times x1 plus a1 times x plus a2 times x squared. This here is how we represent a polynomial in terms of linear algebra. And this is how a computer would represent it, by the way. We're not going to be able to get e to the x. There is no a0, a1, and a2 that will match e to the x. And so instead, here are the normal equations. So now what we're doing is this here, this matrix fills the role of the A transpose A. What this is like our A matrix, but we don't have columns as our basis, we just have functions as our basis. So to compute this, what we call the Gramian matrix, it used to be A transpose A, but now we're not working with A matrices, we're working with polynomials. It is, we take each basis element, and they already make the columns, we also multiply them across the rows. And so this is 1 times all three of those. The second row is x, the second element, multiplied into each of those, and then x squared multiplied into each of those. And so the inner product with functions, remember, was to integrate. And so we're talking about the interval 0 to 1. So we integrate all these things with respect to x and plug in the zeros and the ones into all the right places. And so you see that we get some numbers out of that when we do that. We do the same thing with the right-hand side. Remember, just like we took 1 and multiplied it into all of the rows, and x into into that whole row, x into that whole row, and x squared into that whole row, we do that same thing here, the 1x and x squared in each row with e to the x, and integrating 0 to 1. That's functions inner product. And so when we do that, we do these definite integrals and we get numbers, and those numbers are shown on the handout. Notice the nice pattern that this matrix takes with the fractions, the 1, 1/2, 1/3, 1/4, and 1/5, all in some pretty nice places. That pattern was observed and has a nice place in history, and it has the name of a Hilbert matrix. So then that's a system of matrix equations for 3 unknowns, a0, a1, and a2, and we can solve those equations. And the solution is given at the top of page 9. So those are the coefficients of the quadratic function that would most closely match e to the x.